SwayamPrabha. Digital India. Educated India.
Good morning, everybody. Today we will discuss the concluding part of finite volume method to solve three-dimensional Navier-Stokes equations in complex geometry. If we recall, in the last class we discussed about equation 42. Equation 42 is basically outcome of equation 41 and 39. 39 and 41 both are momentum equations. 39, pressure is at level n plus 1, and then the velocities are advanced at the level n plus 1, and we can call all the velocities are at a level n plus 1 because the pressure is also at a level n plus 1. This is basically the projected velocity. In calculation, what we do not get pressure at n plus 1th level. We get pressure at level n, and then through the convection diffusion equation and pressure contribution we get a velocity which is provisional velocity, and this velocity has not yet satisfied continuity equation in each cell. So these velocity quantities in each cell u, v and w are provisional velocity, and there is a difference between this provisional velocity and the final velocity u, v, w n plus 1. And this difference we can call the velocity correction. If we recall, in MAC or simple algorithm, we have used basically superscript c. Here we have used prime. So this is velocity correction, and similarly pressure at a level n plus 1 minus pressure at a level n, if we subtract we get p prime. This is also synonymous to pressure correction. Then we can, basically what we said has been written here, that up prime is up n plus 1 minus up prime. These u's are all vector u's, that means they signify u, v, w. Then p prime is p n plus 1 minus pn at jth cell or jth phase. And then the corresponding flux corrections. So since the provisional velocities if we use, then the fluxes, that means the mass flux, will not satisfy continuity equation. So we require to correct it, and the corresponding flux corrections will be then on all confining surfaces J summed over east, west, north, south, top and bottom side of the cell equal to minus then again J summed over all confining surfaces F star. F star is basically that uses U stars. So this is equation 44. Now equation 42 and 44 can be simultaneously solved by the following method. This we have already discussed. Assume some guesses for the cell center pressure corrections, which is P prime. Here the suffix P is signifying center of the cell. Use interpolation to obtain the corresponding phase center corrections. That means the corrections that are applicable to each phase. Then at the center of the cell it is PP prime, at each phase PJ prime. Use equation 42, that means this equation 42, to get cell center velocity correction UP prime. Use interpolation to get the phase center correction UJ prime from UP prime and compute the convection fluxes, which is F prime J or Fj prime. So Fj prime equal to then rho Uj prime dot Sj. S is the surface vector for each confining surface and U is the vector quantity, means the velocities in x, y and z directions. Now compute the residual, that means right hand side and the left hand side of equation 44, which is again equation 44. Let us recall. So basically this will be, for a converse situation, this will produce 0. Now RHS and LHS of equation 44. We can use the residual to get new values of correction PP prime. An improved and faster way of doing this involves maybe conjugate gradient method, and repeat steps 2, 3, 4, 5 and 6 till residuals are 0. That is, and in computation getting exactly 0 is not possible. So we will define basically a very small number, a predefined upper bound and a pre-specified small value. Care has to be taken that the interpolation in steps 2 and 4 are done in a manner. So again, let us look at step 2 and step 4. So these interpolations are to be done in a manner such that slow convergence does not result. Experience suggests that from the momentum interpolation, form of momentum interpolation may have to be used in step 4 instead of essentially linear interpolation. So step 4 we may deploy momentum interpolation technique. How to do that? That is what is our modified pressure velocity correction method. Now this step 1 to 6 what we have written, this is working algorithm and we want to make it little more robust, little more faster. So now we go for modified pressure velocity correction method. If the discretized equation for velocity is written as UP star equal to U old minus del T divided by rho into Vp. This uppercase V is the, we have already seen, this is the volume of the cell. So cell P, rho Vp, and these are basically convection and diffusion contributions. Then again delta T, from left hand side delta T has come to this side, divided by rho volume of the cell P. Equation 45. We have to remember equation 45 throughout in order to properly understand the modified pressure velocity correction method. Now UP old, this is obviously the nth time step velocity. Nth UP old means UPN, and SU is the pressure term. We define now, if we can ignore this part, this is a velocity that we are defining. This is sort of we have not worked with it so far. So we define a new variable Vp, again vector quantity, at point P of the cell P, and this has also three components, but this excludes pressure contribution. Many books it is written as mass velocity. But it's matter of definition. We will understand it by the fact that there is no pressure contribution, and this is we will call Vp. Now to estimate the mass flux Fe, we will write rho ue, that means at the eastern phase center, AC at the east phase. Straightforward linear interpolation, when we have done, when we apply linear interpolation, basically the eastern neighbor and the cell of interest P and E, they get involved, and we do interpolation between them, linear interpolation. We have already done it in our second lecture, in our first lecture and second lecture both we have discussed that, and we will mention it here again. This is given by equation 47, where the overbar, so basically that linear interpolation is indicated by this overbar. Overbar symbol means that linear interpolation which we used as equation 16. And what was it? If we recall that at eastern phase center, the quantity phi will be, this is volume of eastern phase, eastern cell, eastern neighbor, divided by volume of eastern neighbor plus volume of the cell of interest into phi p at the center of the cell P, plus volume of cell P divided by volume of eastern neighbor, volume of cell P, total volume into phi E. So this was a linear interpolation. Phi E into this factor, phi P into this factor. Phi P is at the center of cell P, whose volume is Vp. Phi E as the center of cell E, whose volume is Ve. And this interpolation, linear interpolation, kind of central difference, gives us phi E at the phase center. So now what we do, if we look at here, that Fe has to be calculated, and we have done it straightforward through linear interpolation earlier. And now what we will do, we will do momentum interpolation, which means we will do linear interpolation of these velocities which do not have contribution of pressure, this Vp and Ve. So linear interpolation of these two quantities for eastern cell phase and contribution of pressure. And this contribution of pressure is basically the gradient grad P is estimated using pressure at the point P, pressure at the point E, and also other neighbors for a non-orthogonal grid. The role of and this is sometimes this contribution also under relaxed, and the role of this under relaxation with non-staggered grid, because this is collocated grid arrangement, has been investigated by Majumdar 1998. It's a very important paper. I would suggest all of you to read this paper. I will give the reference of this paper at the end of the lecture. The velocity and pressure fields are calculated. So this new algorithm, that Gauss-Seidel type algorithm of Ishwaran and Prakash, that we have already seen, but this modified algorithm, what can be done? But this algorithm is also proposed by them, and here also Gauss-Seidel type iterations are used. So use equation 45 and 46. I suggested earlier 45 and 46. So basically 45 and 46 to compute cell center UP and VP. Make an initial guess of PP, pressure at the cell of interest. Use interpolation of equation 16. Equation 16 means linear interpolation of earlier slide. That means this, what you have written in this here by equation 16, to obtain face-centered quantities Vj and Pj. These are through linear interpolation. Compute mass flux through east face J by using this. So this mass flux, if J star, is rho Vj dot Sj minus delta T grad Pj dot Sj. Use equation Uj prime is delta T by rho grad Pj prime to compute flux correction at phase J. Then this Uj prime is used for, as has been written here, flux correction. So if we substitute minus delta T by rho into grad Pj prime for Uj prime, we get this expression, which is equation 50. Now in each cell we compute this residual, which is basically minus this provisional velocity minus pressure flux, velocity correction flux, and then calculate cell center pressure correction from the relation PP prime is PP prime plus omega into R by alpha P. This is computed using the formulation for diffusion fluxes replacing phi by P prime. So this P prime, just the way we calculated diffusion flux, we will use the same technique, and we have to mention this omega, lowercase omega, is the relaxation factor. If omega is between 0 and 1, it is called under relaxation, that means less than 1, and for omega greater than 1 is over relaxation. And alpha P stands for diagonal coefficients that can be calculated by using alpha p equal to delta t, alpha 1 by delta x1, the western surface, minus alpha 1 by delta x1 at the eastern surface, plus alpha 2 by delta x2 at northern surface, minus alpha 2 by delta x2 southern surface, minus alpha 3 by delta x3 at the bottom cell, and minus alpha 3 by del x3 at the top cell. So this is, there is a small mistake. Please note it down. Equation 53 here, this is not minus, this should have been plus. Please note down this mistake. This has to be plus. So where alpha 1, alpha 2, alpha 3 are basically the same parameters that we calculated in our previous lecture from the basically components of unit normal vector n1 in 3 Cartesian direction, n2 in 3 Cartesian direction, n3 in 3 Cartesian direction, and from there we got basically coefficient matrix multiplied by alpha 1, alpha 2, alpha 3 equal to s1j, s2j, s3j. From there determinants d of the coefficient matrix, and replacing one of the columns by s1j, s2j, s3j, we got d1, d2, d3. So alpha 1 was d1 by d. When in the coefficient matrix first column is replaced by s1j, s2j, s3j, we get d1, and d1 by determinant of d gives alpha 1. Similarly, d2 by d gives alpha 2, and d3 by d determinant the coefficient matrix d gives alpha 3. Now this our residue we calculate then RMS value. If it is less than epsilon, it has already converged. If it is greater than epsilon, then go to step 3 and repeat it again. So store the updated mass flux through cell faces. This is we know this will be the updated mass flux, and store the updated pressure. It will be updated pressure, and store the cell-centered corrected velocity. And cell-centered corrected velocity is this, and then you update the velocity by this velocity correction. Next, go to step 1 and repeat the process until steady state or dynamic steady state is reached. So this residual value, RMS value, will be 0 if we reach steady state. If we do not reach steady state for unsteady flow, usually for unsteady flows the velocities will keep on varying, maybe keep on repeating in a cyclic manner or periodic manner. So under such a situation, we have to reach dynamic steady state. So either we reach steady state or we reach dynamic steady state. It can be shown that satisfying equation 44, that means this summation of the mass flux correction equal to basically summation of F star overall surfaces. That will be basically close to zero. As I said, that zero means steady state, but in numerical computation getting zero is difficult, so it will be less than some predefined upper bound, maybe 10 to the power minus 3 or 10 to the power minus 4, then we have reached the steady state. So it can be shown that equation 44 satisfying equation 44 is basically equivalent to solving del square p prime grad square p prime equal to minus divergence of u star, that is provisionally calculated velocities, by delta t. When u star reaches n plus 1, this divergence of u n plus 1 is 0, so there will be no longer pressure correction. Otherwise, equation 57 is basically Poisson equation for pressure correction. So simultaneously we get velocity correction term. When we get non-zero pressure correction term, we get a velocity correction by done by equation 58, and basically we keep on updating u star through velocity correction so that u n plus 1 evolves, and pressure also is modified through pressure correction so that pressure at the level n plus 1 evolves. The procedure which we have explained here is equivalent to solution of Poisson equation for pressure correction. We have already mentioned that. So after evaluating the corrected velocities and corrected pressure, the final pressure and final velocities, the energy equation is solved with a successive over relaxation technique to determine the temperature field. How it can be done while discussing Mach algorithm we have discussed. See, basically after solving the velocity field, when we go to energy equation, no longer energy equation is nonlinear because velocity quantities in the convective term are known. So solution is relatively easy and it can be done through successive over relaxation technique. The numerical procedure of Ishwaran and Prakash was used, and the detailed calculations were outlined by Prabhakar et al. In another investigation. It was very successfully deployed. Later on, it was again very successfully deployed by Tiwari et al. We can see Tiwari and co-workers, two publications. We will mention in the bibliography or list of references in very complex geometry. Basically, the fluid flow problem was solved, and then the heat transfer problem was also solved. Dalal et al. In 2008 extended this method for solving Navier-Stokes equations using unstructured grid meshes. So basically this is yet another technique. So hexahedrals, when we use, even though these hexahedrals can be of various orientation, various sizes, but their count as IJK are structured. Now, more complex geometries, sometimes it is needed to adapt unstructured grids, because unstructured grids deploy instead of hexahedrals, tetrahedrals, and these tetrahedrons can capture the tortuous geometry, tortuosity more accurately than hexahedrons. So, for some geometries, it is needed or it is desirable to use tetrahedrons. And when we use tetrahedrons, basically it becomes a paradigm of unstructured grids. So solution methodology, what we have outlined, requires to be modified, and that was done by Dalal et al. Now I will briefly discuss about the flowchart. As you can see, grid has to be generated for meshing the geometry of interest, and all XYZ locations of all the points, they will finally describe hexahedrals of various sizes and shapes. But these hexahedrals of various sizes and shapes are the grid. They combine together grid, but the XYZ coordinates, that is the grid data that is to be read. So that conceptually all this hexahedral of as I said, various shapes and sizes are conceptually described, and we can apply boundary conditions suitably. Then initial conditions are set and fluid properties are obviously needed. We solve momentum equation to obtain basically provisionally calculated velocities. Predictor velocities means provisionally calculated velocities. Then we solve the mass balance and basically try to comply with zero mass divergence in each cell, and basically also we correct the pressure, so that we evolve from nth level to n+1th level with correct pressure and correct velocities at a level n+1. These corrections, here solve the mass balance, try to comply with zero mass divergence in each cell, and it results in finally correction in the velocity and pressure in each cell, velocity components and pressure in each cell. So basically there is a loop here. There is like outer loop, there is an inner loop, and we have to keep on correcting velocity and pressure till zero mass divergence, which we indicated by equation 44 is evolved, and then we progress from level n to n+1. And here check the convergence for steady state. If it has reached steady state, we have obtained the final velocity and the pressure field, final velocities in the field and the pressure. If it has not converged, we will repeat the calculation. And having obtained the steady state velocity field, or dynamically steady velocity field, then we have to calculate for unsteady flows, then we have to calculate the average velocities, and with that average velocities or with the final steady state velocities, we have to go for solving energy equation for finding out the temperature field in the domain. Now I will show some sample calculations. This is a reasonably complex geometry, a circular cylinder in a channel. It's not a two-dimensional flow, three-dimensional flow of a circular flow past a circular cylinder, cross flow basically in a channel. Reynolds number 1000, and here what we have shown is little unfamiliar to many. These are called limiting streamlines. So limiting streamlines means projection of streamlines on a surface. So basically this is on the bottom surface. And what is limiting streamline and what is its importance? I have written it here, and you can see not only the stalwarts, the creators of the field, so to say, Legendre and Lighthill. You can get their views about this limiting streamline. There is a special technique to plot the limiting streamlines. As you can see that according to Legendre, the topology of three-dimensional streamlines projected on a no-slip body surface is analogous to experimental flow visualization. And then Lighthill also supported this argument, and these are very strong analytical tools for analyzing nuances of flow. Things like saddle point, things like nodes, etc. in analytical sense can be determined through this. Here you can see basically instantaneous limiting streamlines on the bottom plane, and this is unsteady flow, so obviously it will vary from time to time. And then if we plot the time average limiting streamlines, they will look like this. We will go for another example. This is taken from flow simulation in a module of a fin tube heat exchanger. In fin tube heat exchangers, see, this is a tube and there will be number of tubes. Through the tubes basically hot fluid flows, and it is cooled by the cooler fluid stream, and these tubes are surrounded by fins. So this top plate is a fin, maybe another tube is sitting here, maybe another tube is sitting here. So, and bottom plate is also a fin. So these tubes are surrounded by fins, and through this the gap which we can see, rather through all the gaps, cooler streams flow to basically cool the heated fins and the tube through which hot fluid is flowing. This is another fluid. So this flowing fluid, what we are considering now is maybe air, maybe water, a cooling fluid. And we can see a pair of delta winglets are sitting behind. These delta winglets are also known as vortex generators. So these vortex generators generate vortices and enhance the heat transfer. Now here On the bottom plate, the Nusselt number distribution, which is index of heat transfer, has been plotted, and basically this is color code, but we have used converted the color picture into black and white, but you can see the variation of Nusselt number on this scale, and this gray scale also the variation of Nusselt number is indicated on the bottom surface. This is the location of the tube, and this is the location of the delta winglet pair. Now, having done that, we will mention about the references. As I have already said, the basic contribution of Professor Ishwaran and Dr. Satyaprakash, and other important papers like Professor Cordula's paper, Professor Khoshla and Professor Rubin's paper, Professor Shekhar Majumdar's paper, and all other important papers have been referred here. You can consult these papers for your own benefit. And with this, we have come to the end of our discussion on basically the complex geometry and the fluid flow and heat transfer analysis in complex geometry. We have primarily done fluid flow analysis, and we have been exposed to a very novel algorithm, very powerful algorithm. I would encourage all of you to take up any geometry that you think you would be able to handle, and try to make use of this algorithm. Try to come up with your own program, with your own code, and get the results. And I'm hopeful that many of you would be working on development of codes. For them, this knowledge is very important, but people who would be using codes that are available, commercially available codes or open source codes, for them also knowing the techniques, what is to be done for basically at different stages for implementation of basically different schemes of different orders, or basically how to calculate convective flux, how to calculate diffusive flux, how to correct pressure. These are indeed very important knowledge. I am thankful to you for your interest. I hope your interest will keep on increasing. Thank you very much. Hopefully we will interact again. We will meet again. Thank you.